Hello. So, in the last class we are here. So, till this point we have found out the so many things. First one is that now I know the value of grad g dot n which is nothing but so here it is capital R. Okay, so let me write in the way it is written, capital R dot n divided by mod of R cube. So, this is my grad g dot n. So, it is here, and also I know that that at nth panel. So, that normal is the component, normal component is n k, and also I know it is that my Green's function 1 upon R I. So, I know everything apart, as I said, I know everything apart from the value of phi I. Okay. So, now let us see that how I can get the value for phi I. Now, you see, we understand that phi be the any point on the fluid domain. If phi be the any point on the fluid domain, then phi can be point on the this surface also. So, this phi could be phi 1 also, right. So, therefore, what I do here, that I substitute that phi in phi 1. Now, if I substitute this phi in phi 1, then what is going to happen? Now, if you look at this equation number 10, you can see that I replace this phi as phi 1. So, writing this part as phi 1, and then what I do is here that I take that summation, that now it is maybe difficult for, I do not know, like I said that I equal to 1 and then I not equal to 1. So, it means that I this here, now this I is runs from, of course, I equal to 1 to 12, but it will not run when I is equal to 1. So, it actually started from I 2 to 12. Now, why I said that at this particular moment that I is not equal to 1? The reason is that if you consider our Green's function g equal to 1 upon R, and this R is nothing but that square root of x minus xi square plus y minus eta square plus z minus zeta square. Now, if you put it phi equal to 1, then what is going to happen? So, then in case of this the panel 1, what is going to happen as follows, that you can have at this particular time the definition of R 1, let us say this is nothing but square root of xi 1 minus xi 1 square plus eta 1 minus eta 1 square plus zeta 1 minus zeta 1 square. So, it is equals to 0. So, therefore, 1 upon mod of R, I mean this one is goes to infinity. So, we can have a singularity. So, therefore, we really can't afford this. Practically speaking, we actually we do not cut I equal to 1. Normally, in all this standard software, they do not say that from I equal to 1, if the you can now here you have a name for this point P. Let us now use these names. This point P is called the field point, and this point on this body we call the source point. So, now here normally when you call this summation for the first point phi 1, and we omitting that I equal to first panel, because at that case what is happening, field point is equals to the source point. Now, when field point, now here this is the, this is the critical issues that is coming from lower order panel method, that eventually you are going to deal with how to come out from this sort of challenges. Now, here I put the phi 1 at the centroid. So, therefore, the phi p also actually at the centroid. So, therefore, now you are using the one point Gauss quadrature, right. So, now if you do this one point Gauss quadrature, the meaning is this. So, for one point Gauss quadrature rule, so we have this problem. Let us see what. Now, what is one point Gauss quadrature rule? Suppose you have a panel. So, suppose you have this panel, okay, and then here this is your centroid. So, what one point Gauss quadrature rule says, that you take the functional value at the centroid and then you multiply this functional value with the area. Now, in our case this functional value become infinity. So, we really cannot go with this one point Gauss. However, if you do the that 4 point Gauss quadrature or 4 point Gauss quadrature, in fact, then you can say some other 4 points. So, these are your some, you can say this is your xi 1 comma eta 1 comma zeta 1 and so on. So, all these 4 point is the different than your centroid. So, your centroid, that phi 1, the value of phi 1 equal to xi, eta and zeta, and however, this if you use the 4 point Gauss quadrature rule, the source point, there are 4 source point in that case, and their location is xi 1, eta 1, zeta 1, xi 2, eta 2, zeta 2 and so on. So, really you can have very large value of course, but it is not infinity. So, you can actually do the integration. So, anyway, but we are going with this one point Gauss quadrature rule, because the important part to understand the concept, and let us not go to the integral complexity. Of course, once we understand the concept very clearly, remaining thing is we can deal with later on. So, here that is the idea. I am not considering when the source point equal to the field point. Okay. So, then I use the one point Gauss quadrature rule. Now, it is very easy. My functional value, what is the functional value here? My functional value here is nothing but f I equal to that, what is the distance from the source point to the field point, that is r I. Then I take a dot product with the normal to that particular point, and I divided this by the distance cube. I mean that mod of distance cube, which is r I 3 by 2. So, this is my functional value. So, if I multiply by the area of this particular panel, so I can get the integral value I of the ith panel. Fine. So, therefore, you see I can write this as, remember I am doing for the first panel. So, I can write is alpha p. Now, I can write alpha is the first point. So, I can write it is, you can write as a q 1 alpha at the first point, and why q is meant for the source point 1 q 1 into phi 1. Then this should be equals to summation 2 to 12. So, I can say that I is equal to 2 to 12, and then I can write this as phi I, and I can just simply call as f I minus 1 upon model of r I into, now I can simply k, I just take the top. So, in ith panel the heap mode normal and multiply this by dA I, right. So, this way fine. So, now I just writing in the summation form the whole thing, right. I write everything in the summation form. Now, if I break this summation form, okay, if I break this, I mean writing A1, A2, A3, A3 etc., then what I get? So, this is the written in the summation form, right. Now, if you write it in basically now you call this value as A1i. Now, what is the meaning of A1i? So, here that each point you need to understand. Okay. So, let me explain again that what is called A1i here. Now, I am dealing with here, just let me draw this it is the 12 panels. Now, I am going with this the first panel, right. So, I put my source point which is phi p at the first point, remember. So, since I put it in the first point, so now if I break this equation, how I write? Let me do that. So, I can take alpha and instead of the first point I am just writing alpha 1 and then I write it is phi 1. Then what I get? Now, I get it is now it is going with the phi 2. So, I just write phi 2 and then I said r and then I write it is distance between the first panel to the second panel. So, first panel to the second panel. So, I just write r 1 2 multiply it should be normal at the second point. So, it is n 2. So, it is normal to the second panel divided by, now this r it is again the distance from first panel to second panel. Now, it is mod, right. If I take out the mod, it should be 3 by 2. Now, this whole thing you can what you can see this whole part, you see that everything based on the first panel. Now, similarly, if I write for the third panel, so it is phi 3 and then we have r which is distance from the first panel to third panel and then you have multiplied the normal for the third panel and divided by it is the distance from first panel to the third panel and then whole to the power 3 by 2. Now, dot 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 what happened to the like some arbitrary ith panel? What will happen? It should be the phi I and then r is from the first panel to the ith panel, the distance multiply by the normal to the ith panel, right, and then divided by r one panel to the ith panel and then to the power to the power 3 by 2. Now, you see the everything here basically the common part is 1. Now, if I write this coefficient I can write some coefficient a with the common part is 1 and of course, this varying component is I. So, I can call as A1i, right. So, if I call this A1i, so definitely A11 is nothing but this component and this component I can call as A12 and then this component I can call as A1i, right. So, this is the whole thing actually explained in very short way, we can call this as A1i. So, now you understand that what is the notation I am using here when I call this integration I can call as A1i, right. Okay. Now, see the second one. Now, in case of a second one you know that here, now in case of a first one why I called A1i this one, because I have one unknown quantity which is phi I, right. So, therefore, this first coefficient I can write as phi 1 or phi I into a 1 I, that is how I can write this term, right. I have to use this a I, this coefficient, because this part is unknown to me. If this part is known to me, then everything comes as a number, right. However, here since this is unknown to me, I can only have this part. However, the second part, all the components are known to me. I know the value of R I is nothing but the distance from panel 1 to the ith panel. So, I know what is 1 upon R I, and also I know in this panel I what is the normal component of the kth mode, that also I know. Let us say heap. So, it is ith panel heap mode normal. So, that also known to me, and also I know what is the area of that particular panel. So, that is also known to me. So, all this component is known to me. Now, here this is nothing but your addition. So, that what I am doing? I am adding all the numbers, is it not? Because you see here for the, let us say for the first panel, okay, I mean sorry, it runs from 2 to 12. So, when let us say is I is equal to 2. So, what is the value? Value is 1 divided by distance between the first panel to the second panel. So, this is known to me, and then multiply by the normal let us say heap. So, heap component for the second panel, that is also known to me, and then I have to multiply this with the area of the second panel, that is also known to me. So, this value gives me some number. So, I can call this number is, let us say, my beta 2. So, for in case of a third panel, I can get this, everything again is known to me, and I can call that as beta 3. So on, if I now if I keep adding everything. So, therefore, if I keep adding everything, so I is equal to 2 to 12 beta I, and I call this as B, again it is 1. Why this 1? Because this is I am doing it when I put my field point at the first panel. So, in all equation, when I put my point, that field point into the first panel, so everything with respect to the first panel. So, that is why I called this as B 1. Now, I hope now after explaining this, this equation 12 is very much clear to you. So, only thing I think I missed when I discussed this the coefficient, I missed this, we need to multiply it by the panel area also, right. Okay. Okay. So, now I understand that what is this, right, all these things. So, then this equation, this form, this alpha p blah blah blah, this on this equation 11. Now, if you adjust the sign, now these things, if you take this sign inside the integral component, inside the b1 you take it. Okay. Now, and also this inside the a1 you can adjust the minus sign, because I need everything in classical way, like a1 x1 plus a2 x2 plus a3 x3, so linear equations. So, everything is a additive term, right. So, therefore, now you see that with respect to the first panel, I am able to write one algebraic equation with 12 number of variable, which is the variables are phi 1, phi 2, phi 3 dot phi 12, right. Now, if I practice this with the second panel, now in the next case what I can do is I take this p point, that field point, into the q 2, that means where I define this phi 2. Then how I write the equation? So, now in this case this integration equation should be I is equal to 1 to 12 and then I not equal to 2. See, I am telling you again, it is very simplest way I am doing it. Okay. So, in reality, really we do not ignore the second panel. Okay. But to get the concept, and suppose let us again we try to write a MATLAB code for this particular problem also, that time we are going with this. Maybe it is not close to the reality, maybe the solution may not be as good as expected, but however, it will give you some kind of feeling how I write a panel method code. Okay. So, now here I write I not equal to 2 and I do everything. So, then actually here we can get a second equation as follows, some in phi 1, now everything with respect to 2. So, a 2 2 and in case of a 2 2 ignore it. So, therefore, what will happen that in case of here I just simply replace by it is here I write a 2 1 phi 1 plus alpha 2 into phi 2 plus a 2 3 phi 3, in that way a 2 comma 12 phi 12, and this equals to your B 2. So, I write for 3, I write for 4, I write for 5, I write for 6, right. Okay. So, now you see that how I convert that integral equation into the set of algebraic equation, right. Now, if I do this, then finally, I am getting this systematic linear equation. Now, it is in MATLAB, it is a one liner, you use a function, the solve, you can solve this equation and you can get all this value for phi 1, phi 2, phi 3 and phi 12, right. So, this is the way I will tell you, rather I would like to tell you that this is the crude way or simplest way to find out the solution for the radiation problem. However, if you make this panel really finer or smaller, then I hope you will get more or less reasonable answer for this. Okay. Fine. So, now however, in today we really do not discuss how to compute the influence coefficient more accurately. Okay. As I said that we are going with the 1 point Gauss quadrature rule, mostly we are going for 2 point Gauss quadrature rule or 3 point Gauss quadrature rule or 4 point Gauss quadrature rule, depending on the situation, how the source point and the field point are the orientation of these 2 points. For example, like if your field point is here, this P, and source point is really away Q, then we can use 2 point Gauss quadrature, sometimes 1 point Gauss quadrature also. However, in case of the P and Q are very close to each other. For example, suppose this is your that point P you are putting over here, and if you are trying to find out for your neighboring panel. So, Q is here. So, P or Q is really small. So, in that case we normally we do not use the 1 point Gauss quadrature rule or 2 point Gauss quadrature rule, depending on the situation we try to we are using normally 3 point Gauss quadrature rule or 4 point Gauss quadrature rule. Okay. So, those discussion definitely we will discuss in coming days. Now, here something that we need to take care, like this is something called the aspect ratios. Now, in order to get good results, your panel should be moderately good. Now, however, you can see that these panels are not good panels, because here you can see for this one, this aspect ratio is too bad, right, and here also the aspect ratio is too bad. So, in case of this sort of panel, normally here you can now we are assuming this phi is constant over at the centroid. Now, if it is too elongated, this type of panel, then we can assume that this approximation of phi is like constant over a panel, it might not work very well. And if you take this one, the angle is so large, sometimes what is happening, even is a quadrilateral panel, sometimes in code numerically you can it is as sense as a triangular panel, something like this. So, getting the normals in this case is sometimes not not coming very accurately. So, better try to avoid such type of paneling, and similar for here also. I mean, maybe if it is, you can approximate by some kind of a straight line, not a triangle even. Okay. So, these are the some bad panels, and one needs to avoid such kind of panels. So, then there are is a thumb rule, like the aspect ratio should lie within 0.4 to 1, and then that angle should lie within the 45 to 135 degree. So, these are the thumb rules that if you follow this, then you will get better results. Okay. Now, suppose in your paneling, suppose you are having these issues, then how to deal with. Okay. Now, I will tell you that here if you look, the basic idea is I am replacing the body by distribution of the source and dipole. So, therefore, actually there is no body is there, it is replaced by source and dipole, right. So, therefore, we really do not need that exact definition of the hull surface. So, some small distortion we can accept, right. So, therefore, this is I can like is from my personal experience, I can tell you, like if such bad panels are less than 0.5%, like out of 1000 panels, suppose one panel is like that. So, what you can do is you can ignore this panel, or you can delete that panel, or you can again remesh it, like a bad panel can be replaced by two good panel, like for a two good panel means like suppose this panel is bad panel, let us say. But if you join this, so this become two triangular panel, and we can say that two panel are good panel, right. So, that is what I said, that you can split it further, and so that you can get better paneling. Okay. So, this is all for this day, and we will start the frequency domain panel method, or that how to calculate the coefficients and all, everything is more accurately, that is going to discuss from the next class onwards. Okay. Thank you very much.